Can you make a spoon of sugar jump into the air without touching it? A cake tin with some plastic film stretched over the top. That's all you need. Now, put a spoonful of sugar on there. All right. Make a noise.
Okay, here we go.
And there it goes. Push it farther away and see if it still works.
Let's see about there. Now leave it.
The plastic is vibrating in time to your spoon bashing. It's just like a drum.
Yeah? Yes, I think it's something to do with air vibration.
Must be.
Even right at the other end of the table. And the sugar's still jumping. You're certainly not touching it, so why does it happen? Time to pop into the laboratory. Get the alarm clock going, put the cover on, and start pumping the air out. The clock's still ringing. You can hear it as well as see it. But with less and less air in there, it's getting fainter and fainter. But outside the bell jar, sound is travelling the same as usual. Disc number 2, please, and we'll get some answers to all this. This is a tuning fork. When you knock it, it makes a clear note. I'll slow the prongs down, and you see, they're vibrating and giving the air lots of little pushes. It's making the air move like ripples in a pond, and it's those ripples, those sound waves, that are being carried through the air to your ears. Sound is vibrations, and when they pass through the air and bounce on your eardrums, you hear them. You've got a vibrator in your throat, and if you make a sound, you can feel it. Go on, try it. Feel it vibrating?
Vibrates.
Come on, all of you. Feel those vibrations. Your vocal cords are giving the air little pushes like a tuning fork. They're sending out ripples of vibration, because that's what sound is. Something vibrating to make a noise. Disc number 3, please, if you want to see how human sounds are made. Switching to replay. This is a special X-ray film of a woman's throat. You can make out her pointed chin quite easily. When she starts talking, watch how all the cavities in her mouth and throat alter to shape the sounds. That white bulge in her throat is her voice box. That's where her vocal cords are. And it's a combination of the vocal cords vibrating and the way she shapes all the air spaces around them that make the human voice. Now, sound waves don't just travel through air, they can travel through solid things too. It's an amazing sound, isn't it, Piers? Your turn, Tom.
Sounds very hollow.
The vibrations are travelling along the spoons, through the string, and when you press the knots against your ears, into your eardrums. A long piece of string, 2 tin cans, and you've got the makings of a telephone. It's very easy, and it really does work.
Finished my...
Good big knots at the ends of the string. That's the secret. Stretch the string very tight. You've got to do that so the vibrations can pass along it easily.
What is your best?
Your voice is travelling down the string and being amplified, being made louder by the tin can at the other end.
Pardon?
Now, show me the ruler, please. Yes, that'll do. Is the watch ticking? Put the ruler between your front teeth and bite it. Go on. and block up your ears. Are you ready? Now, Pierce, hold the watch on the end of the ruler. Can you hear the watch through your teeth? You try, Pierce. Go on now. Bite on the ruler. The vibrations from the ticking are going through the metal of the watch, the wood of the ruler, your teeth, and your jawbone. That sound is traveling through a lot of different solid things. Now, can you guess how fast that sound is traveling? I'm switching to replay. A long time ago, some scientists decided to use a small bomb to find the speed of sound. They put it on an island and lit the fuse and carefully timed how long it took for the sound of the explosion to travel across the sea to a neighboring island. Nearly 5 seconds after they saw the flash, they heard the bang. The sound waves traveled through the air and over the water at 331 meters a second. Now that was an interesting discovery, but I think this one was even more fascinating. It was an experiment to find out how fast sound would travel through water. They put 2 boats on a lake. On one boat, there was a pot of flash powder that was set to go off at exactly the same moment as a huge bell was struck underneath the boat, deep in the water. On the other side of the lake, the scientist in the second boat had his ear to a big underwater listening horn. And when he saw the flash, he started his watch and timed how long it took to hear the bell. That experiment has been done many times in many different ways since then. And what it shows is that sound travels through water about 5 times faster than it travels through the air. These days, that fact is used by naval ships to detect submarines in the waters beneath them. Sound waves are sent out from the ship, and they travel through the water and bounce back from the sides of the submarine. Back on the ship, they listen for the echoes that tell them they have found what they're looking for. And by analyzing and carefully timing the echoes, they can even work out how far away and how deep the submarine is. Bats use the same idea. They send out very high-pitched sounds that bounce off the objects around them, and the echoes tell them where they are, so they don't bump into things. Here's a way to see how well sound can bounce. Take the clock, Lear, and put it over there, right at the end, and move away until you can't hear it anymore. Can you hear it? Bit more. Can't hear it? Good. Now, you need the umbrella because you can use it just like a sound telescope to listen for the clock and bounce the ticking right into your ears. Open it up. Hold it on the side of your head, away from the alarm clock. Listen carefully. Does it work? The ticking is travelling through the air and the sound waves are bouncing off the tight skin of the umbrella. The shape of the inside of the umbrella focuses the sound into your ear. That's why you can hear the ticking again. An umbrella makes a very good sound collector. It works like a large ear. After all, that's what your own ears are for, collecting sound, and that's why they're the shape they are. I see the next experiment's nearly ready. Let's get on with it then. Make sure the card is propped up nice and straight. The sound waves will bounce off that. The two cardboard tubes are for transmitting and listening to a test sound. Set them at an angle to each other. They shouldn't touch the card. And now this is where the clock comes in again. Put it at one end and listen at the other. The ticking of the alarm clock is travelling down one tube, bouncing off the cardboard, straight into the listening tube, along that, and into your ear. The ticking is making the air vibrate in the tubes, and that's what's carrying the sound. You have a go, Tom. The sound is reflecting off the board just the same way as light reflects off a mirror. It's the way sound bounces along a tube that makes a stethoscope work. The doctor's got one, but well, this is just as effective, isn't it, Leah? Can you hear the noises from inside Syria? They're being collected up by the funnel, and then the sound waves are bouncing and vibrating along the inside walls of the tube. Can you hear her heart?
Haven't you heard it yet? No, I can't find it.
Well, while you're trying to find it, here's an experiment that shows just how strong sound waves can be.
There. Now, ping pong ball.
The idea is to hang the ping pong ball so it is just touching the side of the bell. Now ring it. I know it looks as if the clapper had made the ball bounce, but you'd be quite wrong to believe that. Now hit the bell from your side, Piers.
It goes round. Try it like this.
See?
Stephen does it.
It's the sound waves from the bell itself that are making the ball bounce. Yes, that's exactly the same principle again. The glass is ringing because when you do that with your finger, you're making it vibrate, just like the bell did. If you've got a balloon, there's another way you can see that vibration happening. Now squeeze the neck. See how it vibrates? And listen to that terrible noise those vibrations are making. The neck of that balloon is vibrating a bit like your vocal cords do. Just look at this. That balloon slowed down many times. See those vibrations as the air comes out? It's those vibrations that are making that awful noise. Piers, it's your turn again. Please will you ring that bell? No, really ring it. Louder, louder! Now, I mean really louder. Now, sound is a form of vibrating energy. So the more energy you put into making a sound, the louder it will be. Thank you, Piers. My assistant has got some special equipment in the laboratory that makes sounds and then analyzes them. This little television screen is showing the kind of sound waves she's investigating just at the moment. As she changes the note to make it lower, the sound waves get longer. When she alters the volume and makes it louder, the sound waves get bigger. And when she switches the sound right off, there are no sound waves at all. And on again. Most instructive. Switching to replay. Sound waves spread outwards from whatever is making the noise. But what happens to sound waves when the thing that's making the noise is moving very fast, like an airplane? Look at those sound waves in the front. They seem to be getting squashed up. Listen to this. Did you hear the sound change as it passed? The ambulance is bunching up all the sound waves in front of it so the note is higher. And as the racing car passes, the note gets lower because the sound waves are spread out again. The scientific name for that is Dopler shift. And with a bit of hosepipe and a whistle stuck in the end like this, you can bunch up sound waves yourself and hear the Doppler effect. It's not that easy, I must say. You need a lot of puff. You have a go, Celia.
Okay, it's your turn. Oh, look. Oh. What's it like? Difficult.
Listen to the way the sound rises and falls. Well done. Of course, musical instruments are all about the pitch of sounds. You can make your own experimental instruments out of all sorts of things. A baking tin, a bit of wood, some elastic bands stretched tight. That's it. Don't forget the bridge.
Got to get these two strings between those two little blocks. Carefully. Look at that.
And there, you've made quite a good guitar.
Oh no. Yeah, do it.
Do you know how to alter the pitch of the notes?
Make some funny sounds. Try the bits behind.
Just a moment, Piers. Yes, Tom, you make the string shorter and tighter.
Oh gosh.
Now look at this. Switching to replay. This is a Spanish guitar in slow motion. You can see how the low strings vibrate quite slowly, and the high strings, which are much tighter, vibrate very much faster. Now, let's use air to shape the kind of musical note you want. Blow across the top. Now, empty some water out and do it again. The pitch, that is the note, has gone down, hasn't it? Pour some more out. That should do it. Goodness, that's gone very low. It's the length of the column of air in the bottle that changes the note. The longer the column of air, the lower the pitch. And it was the air that was vibrating, not the bottle. Here's a puzzle. See if you can work it out. Switching to replay. The ringing glass again. The water goes in, the column of air inside gets less, but the note is going down, not up. Solved it? It's not the air that's vibrating, it's the glass. And as it fills, the water vibrates too, so the note gets lower. Back to columns of air. That's why wind instruments work. You know, trombones and trumpets. And what's this?
A xylophone.
Yeah.
It's also why these things work the way they do. Bits of pipe of different lengths on strings, and listen to the noise they make. Short lengths, high notes. Long columns of air, low notes. The longer the column of vibrating air, the lower the note. Now, those swanny whistles, very neat. They work on just the same principle too. The longer the column of air in the whistle, the lower the note. The shorter the column of air, the higher the note. In fact, the higher the pitch. The best music ever written, the sweetest singing you'll ever hear, every single sound in the world, they're all just vibrations pushing against your eardrums. Now, there's a thought. Seems to me you have all the makings for a good little orchestra there. You've got swanny whistles, the drums, and the tubular bells, don't forget the guitar, and a comb and tissue paper for Lear. Come on, let's get those vibrations going. The echoes ringing, the sound waves blending. What are you going to play?
Ready? 1, 2, 3, go.
Haven't danced for ages. What a treat. Don't you absolutely adore the waltz?